So I'm a chemical engineer. I have spent a lot of my career doing chemical process development and have worked with a lot of these gases. And I volunteered to do this course because I want to make certain that people stay vigilant, stay aware, don't get complacent about a lot of these hazards. These liquefied gases are vital to our economy. There are a lot of suppliers and industry associations that provide a lot of information. I just passed around some information from the Chlorine Institute, and this is an example of one I wanted to make certain that you knew about. And in general, people do a great job in managing these risks, but we still have problems. We still have fatal accidents. We still have very serious injuries, and we've got room for continual improvement. So I want to make certain that people understand the hazards and what controls are out there and how standards have been evolving to address improvements in managing the risk. And so this is the third in the 4 series of sessions here today, and I'm going to talk about primarily chlorine. I'm going to talk about oxygen as well, though, just because it is one of the major liquefied gases when it's under cryogenic conditions. And for those of you who are not here this morning, we talked about the issue of what is a cryogen and what is not, and the fact that oxygen, for example, if it's in cryogenic conditions at low temperature inside the cylinder, it looks like this. It is a liquid. At room temperature, no matter how much pressure you put oxygen under it, it is going to be a gas. It's not going to have a liquid phase because it's above its critical temperature. So those of you who want to learn more about that, go to session number 1. Chlorine is an example of something that we can't live very well without, but it is extremely hazardous. There are very few substitutes. There are some situations where we can use chlorine in a slightly different form, and I'm going to talk about that. But in general, chlorine is something that's vital to our economy. It's vital to public health, and we have to be able to manage the hazards that are associated with chlorine. And we, in general, do a good job at that. For those of you who weren't here, while I talk about a lot of different gases, my focus is on the big 3 in terms of large volumes. These 3, with propane being the primary flammable gas that pulls people under the EPA RMP requirements, or CalR, for process uses. These 3 account for well over 90% of why people file RMPs nationally, as well as probably in California. The Chlorine Institute is a very good example of an organization that provides a lot of very good information to first responders, to chlorine users, to system designers. And I want to encourage you to go to their website, which I've referenced numerous times in these slides. And I've also shown you that brochure. Now, I don't know if everyone, I think I only had about 25 copies that I picked up from a speech by someone. And this, I'm going to show you a video that they hand out for chlorine emergencies, an overview for first responders. And this is also free from the Chlorine Institute, and I think it's actually distributed through the American Chemistry Council, which the Chlorine Institute falls under. And if someone really wants this badly, I've got a number of these at home, so you can, if you want to come up, if you really want to know more about it and you want to get a copy right today, you can have my copy. I spent a lot of money, it's free. Here are some examples of the technical literature. Is all you have to do is register on the website, download these free as PDF files, and they have a wealth of information about how to install proper piping systems for dry chlorine systems, chlorine vaporizing system, chlorine pipelines, emergency response, first aid, properties, the basics about chlorine. There are ones that talk about chlorine scrubbing systems. We're going to talk, one of the examples I give today is about a scrubber that did not work properly. Recommended practices for facilities in terms of how to prevent releases. And as I mentioned this morning, one of the major roles of chemical engineering with dealing with hazardous materials in process safety is prevention of loss of containment. In your elevator speech, if someone asks you what's the difference between process safety and worker safety, process safety is all about preventing loss of containment through engineering controls and management system processes. And there's a big difference between worker safety and process safety from that respect. Again, some other things about the Chlorine Institute. Chlorine Institute also provides information on HCl and anhydrous HCl and on bulk transport and learning from experience events and so forth. So there's a lot of information also for water and wastewater system operators where there's a lot of chlorine used in ton cylinders typically. So instead of me going over all of this business about properties of chlorine, what I'm going to do is give you an example of what the Chlorine Institute provides.
Physical, and reactive properties of chlorine.
So would someone
Chlorine exhibits a very strong, pungent odor that is similar to bleach, but is much stronger. It is easy to detect by sense of smell at very low concentrations. By itself, chlorine is non-explosive and non-flammable, but it is a strong oxidizing agent that will support combustion with flammable gases and vapors. If chlorine comes in contact with combustible substances, explosions and fires may result. The most common way for chlorine to come in contact with incompatible substances is through spills, releases, and container failures. Hazardous conditions can also result if chlorine comes in contact with any of these substances. Chlorine reacts readily with many organic chemicals, often violently. Chlorine reacts with water to form hydrochloric and hypochlorous acid. It is also incompatible with moisture, water, and steam, forming corrosive acids when mixed. At 483 degrees Fahrenheit, chlorine will oxidize steel, essentially burning it. Chlorine reacts with steel at lower temperatures under certain conditions. Oxidation could lead to a fire, which should be avoided since water cannot be used on a chlorine fire. Chlorine exists as a gas or a liquid. This chart compares the properties of chlorine gas and liquid. Again, it is important to remember that gaseous chlorine is heavier than air, so it will settle in low areas such as basements, creek beds, and ravines. Liquid chlorine becomes a gas at minus 29 degrees Fahrenheit at atmospheric pressure. Liquid chlorine has a clear amber color, while chlorine gas will exhibit a faint yellowish color at low concentrations to a greenish yellow to green at high concentrations. Depending on the humidity, chlorine gas is usually not visible at concentrations below 25 parts per million.
Okay, for those of you who were here this morning, here's the, so you know that the molecular weight, so you don't have to remember that factor of 2.5. If you know chlorine's a diatomic gas, you know the molecular weight is 71 for the diatomic gas. So what was the rule of thumb in terms of density relative to air for the vapor? The ratio of molecular weight of the gas to the average molecular weight of air, which is roughly 29. 71 over 29 is about 2.5. So that's a good rule of thumb to remember. Now, another important point. One of the reasons that chlorine has such great commercial value, not only because of its chemical properties, but because of the physical property that's shown right there. Again, for those of you who weren't here this morning, there are certain gases that cannot exist as a liquid at room temperature. And that's because that is above their critical temperature. Now, chlorine has a critical temperature of 144 C. It's pretty high. So that means that when you've got a tank car or tank, this is what's inside. A tank's under pressure. It's at 70, 80 degrees Fahrenheit. It is there as a gas, as a liquefied gas. And that has some advantages in terms of transportation because it's a very dense phase. Also, it presents some challenges in terms of the hazards, because what happens with a liquefied gas when you suddenly release the pressure? It expands rapidly, a very rapid phase transition, and that leads to the condition that's called a BLEVE, boiling liquid expanding vapor explosion. So we're going to talk about that too. Now, vapor pressure versus temperature. When you have a liquefied gas, if you know the temperature, if you've got that gas container and if the pressure gauge isn't working, just knowing the temperature, that's all you have to know. And then you look at the vapor pressure versus temperature relationship and you will know what the pressure in that vessel is. Because for a pure liquid, at any given temperature, it is going to exhibit a certain vapor pressure above the liquid solution. Vice versa, if you know what the pressure is, you're going to know what the temperature is, assuming it's in equilibrium. And this has some importance in terms of emergency response at times. Now, effects from chlorine exposure. Exposure to 1 to 3 parts per million provides mild irritation of the nose and throat and so forth. And the reason for that is that it reacts with water and forms hypochlorous acid and hydrochloric acid. Very corrosive. We're going to be talking about ammonia later. There is an order of magnitude difference, order of magnitude, factor of 10 difference in terms of lethal concentration between chlorine and ammonia. Chlorine has a lethal concentration. If you get up into the hundreds of parts per million, roughly 400 parts per million, short-term exposure, you will be dead in a very short period of time. The death is a result of primarily pulmonary edema, but you'll also have other effects as well. As you go up, the numbers I've shown here, headache and throat irritation at concentrations of 5 to 15 parts per million, 30 parts per million produces immediate chest pain and so forth. So once there's a release, the concentrations can go very high in terms of concentrations, short distances from ammonia releases or chlorine releases. We're talking about 40, 50,000, 100,000 parts per million. So, you know, those are well above the lethal concentration level. So if you get into a cloud, it can be the last thing you will ever do. So it's a very serious situation. Now, one of the things I'll mention here, IDLH, here are the chlorine exposure limits. And again, this is all in these DVDs that are provided by the Chlorine Institute. And it's also in a lot of information that's available from NIOSH and the CDC, etc. As you see, the exposure limits are on the order of 0.5 to 1 part per million for permissible exposure limits. Ceiling limits are not much higher. And then down at the bottom, the IDLH, immediately dangerous to life and health. That particular number confuses a lot of people. Someone want to explain to the rest of the crowd here, if they want to participate here, how were IDLHs developed? Does anyone know what the reason for them is and what the rationale is? Are you going to keel over immediately if you're exposed to that level? Close, 20. Yeah, that's right. And so this, it says immediately dangerous to life and health. This does not mean that you are going to die from exposure to that level, but it means you're going to be real uncomfortable, and it will limit your ability to escape, especially things like chlorine and ammonia that affect your eyesight because of tearing and your ability to breathe and coughing and so forth, and respiratory distress. But you will be able to escape at these levels. Now it's interesting, the ideal H value for chlorine used to be 30 parts per million. It was changed in the last 10 years. I don't know exactly when it happened, but now it's 10 parts per million. I'm going to, during the course of this discussion, describe some incidents and talk about situations where people may have been complying with standards where standards were not adequate. And one of the things I emphasized this morning is I, along with a group of about 9 other people, we teach a course through the Center for Chemical Process Safety on risk-based process safety. And our belief is that you need to manage risks like these liquefied gases based on the particular situation you're dealing with in terms of risk exposures and what the consequences could be, and not depending solely on standards, which may not be adequate. And there are situations where people have met standards and have still had catastrophic events. And I'm going to talk about incidents where there are ways to minimize the risks of use of chlorine. I'll give you a specific example related to the Valero refinery that we discussed on the propane deasphalter fire in the last session in the morning. I'm going to talk about some transportation accidents and accidents at storage and container filling facilities, and also some accidents in doing transfers from different types of transport vessels. And a lot of these kinds of activities take place at facilities within your jurisdictions. And hopefully, and I'm guessing in most cases, there have been very few incidents, because in general, chlorine is handled very safely. But there are still fatal accidents that happen all too frequently. Now, at this Valero McKee refinery that was the site of this propane deasphalter fire, where propane line ruptured and there was a jet fire, one of the side effects from that fire was that there happened to be 3 one-ton chlorine cylinders in the vicinity of this propane deasphalting unit. And these propane cylinders overheated, the pressure relief devices relieved, and in one case the tank ruptured. And so I'm going to show the video that discusses this particular incident. And we're going to go 9 minutes in. I had it set to the right spot, but it's not there, but I know where the right spot is.
On February 16, 2007, a massive fire broke out in the propane deasphalting unit at the Valero McKee refinery near the town of Sunray in the Texas Panhandle. 3 workers, including a contractor, suffered serious burns. 11 others received minor injuries. The fire occurred after liquid propane was released from process piping in a fire protection guidance to require the use of remotely operated shutoff valves and more extensive fireproofing of structural support steel near refinery process units where jet fires can occur.
Valero used chlorine as a biocide to kill bacteria in cooling water. This chlorine was stored in a hazardous area where it was exposed to the threat of fire. Refineries don't have to use chlorine. There are inherently safer chemicals, such as bleach, that can be used for this purpose.
3 one-ton chlorine containers were in a shed only about 100 feet from the deasphalting unit. The intense heat ruptured one of the containers and melted the fusible plugs on all 3, causing a release of chlorine. Valero reported subsequently that more than 5,300 pounds of chlorine were released to the atmosphere. The toxic gas could have presented a serious threat to responders had they not been evacuated earlier. A second catastrophe could also have occurred.
Now, it would be nice if there were an easy solution, like is described there, to eliminate elemental chlorine use and to use a less hazardous form of chlorine. While that is possible in the case of using chlorine as a biocide, to use it in the bleach form, to essentially react chlorine with sodium hydroxide in aqueous solution to produce a solution of sodium hypochlorite, you can't do that in many cases. So it's not an option from a risk management standpoint to eliminate the use of elemental chlorine. So that we've got to deal with the hazard. We've got to keep that chlorine in the tank car, in the pipeline, in the process, and prevent it from getting out and exposing workers and members of the public. So how is chlorine transported? Chlorine is a very large volume product transported around the U.S. and used in quantities of on the order of 12 million tons per year. It's transported by a number of means. As shown on this slide, there are chlorine barges that have very large individual pressurized tanks, like 4 of these very large tanks, and they may have in excess of 1,000 tons of chlorine capacity on a single barge. And those barges move in many of the inland waterways around the U.S. Railroad tank cars are a primary method for moving chlorine around the U.S. 55 or 90-ton tank car loads. Tank trucks also move, much less is moved in tank trucks, in up to 20-ton cargo shipments. One-ton containers, as was shown there in the McKee refinery fire, and then 100 to 150-pound compressed gas cylinders. And in those compressed gas cylinders, there are also, in all these cases, it's transported as a liquefied gas. So what's the Chlorine Institute say about the industry's safety record for chlorine transport? Well, they say it's been pretty good. And they say that rail transport is one of the safest modes of chlorine transport. Some 3 million tons of chlorine are shipped by rail annually, typically in 90-ton tank cars. This amounts to over 30,000 tank car shipments a year. Of more than 1.5 million chlorine tank car shipments since '65, there have only been 11 breaches of tank cars, incidents where chlorine escaped into the air because of damage from an accident. I don't think that includes the minor leaks that occur at the tops of the tanks with the valves. These are very large breaches. Overall, accident rates for rail shipments of all hazardous materials, including chlorine, have declined 88% since 1980. And remember, I talked to you this morning about some of the changes that were put in place after the levee at the site in Arizona with the propane tank, with the top and bottom holds on the couplers, and the insulation in the front and on both ends of the car having shields essentially welded in place to prevent penetration of the ends of the tank car. So there are a lot of reasons why things have gotten better. But that doesn't mean people are not still dying from transportation accidents involving chlorine. Now here's some accident statistics that the Chlorine Institute cites. In 2011, the total number of rail incidents reported was less than 0.89% of all hazardous materials rail incidents. It was less than 0.028% of total chlorine shipments. So it's pretty good. And there's also work underway because it's not perfect. So the Department of Transportation and various major producers of hazardous materials, such as the producers of chlorine, have a vested interest in looking at how can we continue to improve from an engineering standpoint the reliability, survivability of these transport vessels in terms of surviving crash conditions. Now, as I mentioned, one of the things that happened after some levees with propane tanks was putting shields on the ends, the front and back ends of tank cars. But what if you have a side impact? If you have a derailment and you have cars flying all over, and I'll show you in the ammonia discussion such an accident, you can still get side penetration. And so there's work underway looking at how to improve the overall performance. And studies that were done in the late 80s and early 90s, they showed that many of these tanks can survive accidents where there may be a decoupling and there may be a penetration of one of the couplers through the insulation, but they can still survive at 18, 20 miles per hour. Higher than that, maybe they won't. So they're looking at how to better design these tank cars. Now, will that be a quick fix? What's the lifetime of a tank car? These tank cars aren't automatically, when a new standard's put into place, replaced. So it takes years to often turn over the inventory of what's out there running across the rails. So we've had some big improvements in the last 30 to 40 years in terms of levee incidents, but there's still some improvements and people are working on these kinds of issues. So let's talk about in the supply chain, and we're going to be talking about from production through distribution, distribution centers and so forth. Where do accidents occur? One large release happened in Henderson, Nevada in 1991 at a chlorine production facility run by Pioneer Chlor-Alkali. At this incident, they released roughly 70 tons of chlorine, which is equivalent to what is typically in a railroad tank car. And this happened in May of 1991. There were quite a few people who went to hospitals. 30 were admitted for treatment. Luckily, no one was seriously injured and no one died from this event. At the facility, they had 8 150-ton storage tanks, and what happened was they had a line leading from a tank going to a pump that was used to fill railroad cars. In other words, this was a production site. They produced chlorine, these tanks were used to store product, and then they would fill rail cars and ship rail cars out, and this was probably the source of chlorine for much of Southern California, I would guess. There were a number of issues with this in terms of how the employees assessed the situation, how quickly they responded, and how they notified the authorities and how they interacted with the authorities in terms of addressing the issues. They very much underestimated the severity of the situation, and it got out of control. They thought they had it under control several times, and they probably did not have a good mechanical integrity program. They did not have good emergency planning. They weren't prepared to deal with the issues that they should have been able to deal with in a much more effective manner and shut down the flow before it got to the situation where over a period of 24 hours they lost 70 tons of material. Now, what could the consequences from 70 tons of chlorine gas release be in a metropolitan area? There have been numerous studies done with numbers anywhere from 10,000 to over 100,000 fatalities. This is real serious. It could be a major catastrophe. What's the largest toxic gas release from a process plant incident that happened in history? Bhopal. How many people were killed? 6,000. Over 10,000. One of the reasons the Center for Chemical Process Safety was founded in 1985 by the American Institute of Chemical Engineers, and one of the reasons that I wanted to become a consultant when I retired to that group was to hopefully prevent any kind of accident like Bhopal from ever happening again. Railway tank cars carrying 70, 90 tons of chlorine can potentially have those kinds of consequences. So that's why I want to come and talk about these issues so we never become complacent with these kinds of hazards. As a society, as an industry, as a chemical industry, we have a very good record in managing these risks. It's not perfect, and we need to continue to try to get better. Transport. I did a little search because I didn't know of many incidents with chlorine barges, and luckily there haven't been many major incidents that I at least have been able to find. In March of 1991, a barge did sink in the Mississippi River near Natchez. It was left on the bottom of the river for 18 months until the river conditions were such that it could be raised. There was a lot of public controversy around this situation, and finally President Kennedy ordered the Corps of Engineers to work with a number of other groups, and they raised this barge successfully. During this whole process, they provided to the public something like 8,000 or 10,000 gas masks in case these tanks failed when they were removing the chlorine from the barges. So again, this is a success story in that these tanks survived the sinking, the raising of the barge, and then unloading. Good engineering design. Or were they lucky? Hopefully it was good engineering design. Runaway chlorine barge, 1972 on the Ohio River. That is a barge about ready to go over the spillway near Louisville, Kentucky on the Ohio River. So I just want you to know, these things happen. These things, this again had a good ending. They were able to get in there and unload that barge. Now, I'm not sure I would want to be on the vessel that went to do that unloading, but they successfully did this. But again, these kinds of incidents happen. 2004, McDonough, Texas. June 28th. Head-on collision of two trains resulted in a chlorine tank car breach. 3 persons, including the conductor of the UP train and 2 local residents, died as a result of chlorine gas inhalation. We've got to keep it in the tank. Loss of containment. The National Transportation Safety Board determined that the probable cause of the June 28, 2004 collision of Union Pacific Railroad train with this other BNSF railway train was train crew fatigue that resulted in the failure of the engineer and conductor to appropriately respond to the wayside signals governing movement of their train. Now, in the discussion we had this morning of the propane incident in Italy at night, remember what I said when they did the modeling after the incident? From the time the collision occurred and the derailment until the explosions occurred, 90 seconds of time, and 30 people were dead. There's not much time to react, so there are 2 types of safeguards we talked about, preventive and mitigative. Preventive safeguards, which are typically engineering controls, are intended to lower the probability of release. Mitigative safeguards are intended to mitigate, to reduce the severity of consequences. In these kinds of transportation accidents, we don't always have a lot of time, depending on where it happens, to mitigate. So prevention is what we've got to focus on. Graniteville, South Carolina, January 2005. Misplaced track switch resulted in a collision between a railroad tanker carrying chlorine and another parked train. One of 3 derailed chlorine tank cars ruptured, venting 90 tons of chlorine gas. 41 were hospitalized. 9 fatalities. We're lucky it was only 9. Could have been 9,000. Many surviving victims developed significant pulmonary signs and severe airway inflammation. 41 people were hospitalized with acute respiratory distress syndrome. I'm not certain in this case what that extent means, but acute respiratory distress syndrome usually means you go on a mechanical respirator for 24 to 48 hours, and if you make it that far, you may survive. But this is a very serious type of event when these happen. Close call, August 2007. Operator error caused a Union Pacific tanker car full of chlorine, probably 70 tons to 90 tons, to escape from the Arden train yard near Las Vegas. Although no toxic gas was released, the tanker car traveled 20 miles on its own through densely populated areas before railroad workers and the police were able to stop it. Based on prior estimates by the University of Nevada and by numerous other groups, this is, and again, the number, I've seen these numbers, anywhere from 10 to 100,000 could have died. Now, this isn't a transportation accident. This happened after the tank car got to the siding. In the case of chlorine transport and use, many facilities that utilize chlorine on site may use the tank car as their storage tank. Or they may keep multiple cars there for some period of time in their inventory. So DPC Enterprises in Festus, Missouri had this incident in August of 2002. This morning I talked about there are 4 steps in a risk management business process. The first step is identifying the hazards and knowing what hazards you have. The second is to evaluate those hazards in terms of consequence analysis and probability of events, to come up with some risk rating. And based on that risk rating, then to take actions in terms of implementing risk controls. That's the third step. If you're then satisfied that the risks are tolerable, then you implement and you go and maintain those controls. If you're not satisfied, you iterate back, look at other control options, and once you're finally there in terms of being satisfied, then you go and operate the facility. This company did a lot of things right. They got through. They had a business process. They did those 4 things right. Now, they also had some challenges. This is a company that brought railroad tank cars of chlorine to a siding, like there. And then they would fill storage tanks on site or directly fill 1-ton cylinders and other cylinders of chlorine. As indicated here, they had 4 packaging operators and 4 truck drivers and 2 administrative staff, 12 full-time personnel. Probably none of them were chemical engineers or mechanical engineers. Probably none of them had done a process hazard analysis like I go out and help teach. So these folks had some level of appreciation for the hazards they were dealing with. But they probably weren't real savvy. It's a 1-shift operation, typically running from 6 a.m. to 4 p.m. Monday through Friday. This was located 35 miles from St. Louis. One of the fellows I teach this process safety course at the time was the lead investigator for the Chemical Safety Board and actually did this investigation. So he's told me this story many times. DPC had learned from past events. One of the things that we talk about is learning from experience is one of the key elements within a management system. Again, these folks had that part right. They said, gee, there have been a lot of other companies in the chlorine business who have had accidental releases. So we're going to put some safeguards in place so that if we have a release or we have a failure of one of our flexible hoses, if we have an accidental decoupling of our fittings for the transfer, we're going to be able to automatically shut down. We'll lose a little chlorine, but it's not going to be a big deal. So they went along and thought everything's great. We've got all the controls in place. Now, what they had done, because of the known limitations of emergency flow control valves for situations involving leaks and unloading hoses. Excess flow valves is what, excuse me, I said emergency, it's excess flow valves. Tankers that carry hazardous materials like chlorine, like propane, like ammonia, have internal valves that if the flow rate goes to a certain level, they will automatically shut, or at least close to a very low flow level. However, they have to be triggered. In the incident that I described had the video for this morning in Iowa for that 18,000 gallon propane tank, they had piping connected to the outlet that was protected by this excess flow valve that restricted the flow so that it would not close the excess flow valve. So you cannot depend on these excess flow valves. What these are designed to do is if you have a rollover incident with a transport tank like this, and you've got this shield on the top that protects the external valve. Under that valve is a second valve. So this is engineered, you've got double jeopardy. You lose the top valve, you've got another valve, so you'll start getting flow, and it'll be high flow, and this other valve will automatically shut. But it has to be a high flow in order for it to work. So what did they do? They had this automatic shutdown capable of isolating the unloading system in 8 to 10 seconds. Emergency shutoff switches to activate the shutoff valves should be installed at least 2 easily accessible remote locations. And leak detection equipment that either automatically activates the shutdown or alerts personnel to manually do it. So they had all this in place. They also had transfer hoses. These transfer hoses were braided metal layer over a Teflon inner liner with a spiral high-density polyethylene guard. Although hoses with non-metallic cores, such as Teflon, are more tolerant of moisture, they are subject to permeation by chlorine. So some chlorine does permeate through this, and it will lead to corrosion of the metal braid, which provides the protection against high-pressure operation and keeps the material in the PVDF material. This braiding was supposed to be made of a different material. It should have been Hastelloy C276. Now, what actually happened? So what happened was that one of these hoses failed. And that was supposed to, they had an automatic shutoff that within 8 to 10 seconds should have shut this down. They should have lost pounds, tens of pounds of chlorine in this release. They released 48,000 pounds over 3 hours. How did this happen? The release affected hundreds of other nearby residents, and the community was advised to shelter in place. Luckily, this was in a relatively low-density inhabitation area. Traffic was halted on Interstate 55 for an hour and a half. That pleased a lot of people. And 3 workers and 67 residents had to seek medical treatment for minor injuries, but they were luckily minor. During the initial response to the release, there was considerable confusion. Plant staff did not have instruction and mechanisms for community notification. It was chaos. And local emergency response personnel were not prepared for an incident of this magnitude. Remember, one of the things I mentioned this morning that is not under OSHA PSM or EPA RMP plans is stakeholder outreach. If you are an operator, it is your responsibility to have community outreach, to make certain that first responders know what the magnitude of the hazard is at your site and how to respond to that emergency in cooperation with you as the owner-operator. It is also the responsibility of you and the regulatory community to understand these things and to, if they do not volunteer, that you go out and work with them to make certain that you understand what these hazards are. Turns out that these braided hoses, investigators determined that although the hose manufacturer's records and the hose ID tag indicated that the metal braid on the failed hose was made of the material in the specification, Hastelloy C, it was actually made of stainless steel, which looked exactly the same. So this was a manufacturer's error in terms of quality control, and there was no control internally to make certain that the material as received met specifications. And I'm guessing that none of the 8 or 12 employees at this site even knew the difference between Hastelloy C and stainless steel, and probably furthermore didn't even know that there was a standard for what they should be installing with that hose. Should they have known something about that? Yes, they should have. Should the corporation have had a quality control system in place? Absolutely, they should have. Yes?
What would that quality control process be if the hose that they received was marked as being made in Hastelloy? Should they test the metal in all their hoses, or what is their process? What would that process be?
It would have to be put back, the responsibility would have to be put back on the original supplier. And after this event, I am certain now that the Chlorine Institute and all of the distributors have instituted such more rigorous requirements for quality assurance and certificates of analysis. That's what's typically done, is that for safety critical devices or safety critical materials, like in the drug industry, certificates of analysis are issued for every batch, where there's an actual identity check done to make certain that the material is what was specified.
And then that would come with the piece when you buy it.
Correct. I'm not going to go into the details of exactly how this failed. There's a lot of engineering details why there were other problems with this system. Now, on the day of the incident, even though the chlorine detectors detected the release and the operators pushed the shutdown button, so they had been trained on doing that. So my colleague, who actually did the investigation, went out and asked the operators, now, do you do routine checks on the system? Oh, yes, we do it all the time. How do you do those checks? Well, we push the button and listen for the solenoid. Well, the solenoid was actuating, but it wasn't moving the valve mechanism. So they weren't actually, what the check they were doing, remember I said there's a 4-step process. The last one, in mechanical integrity, is doing inspections, testing, calibration, and maintenance to make certain that safety critical systems, including those for emergency shutdown, work as designed and specified. So again, they were doing it partially right. They'd put in controls. They were testing them, but their testing was faulty. They weren't actually verifying that they were working. They thought they were working, they were not. So we had lack of quality control, we had a lack of effective inspections, lack of adequate testing and maintenance by DPC on chlorine transfer shutdown control valves to ensure that the systems worked. Now in the next segment, a very similar system to this in France on an ammonia system also failed for a different reason. We'll talk about that in the next couple hours. So there are a lot of reasons, but it all comes down to why did this fail? Lack of management systems. Root cause, lack of management systems. And not fully appreciating the magnitude of the hazards and how important safety critical components are, like flexible hose. How many of you know about the phosgene accident from DuPont that happened at a DuPont facility about 2 years ago in Bell, West Virginia? A number of you. Failure of a hose, right? Same thing, flexible hose connected to 1-ton phosgene cylinders. They had a maintenance requirement as part of their management system for process safety. And here is a company that I personally have held on a pedestal for years and still do, as being a great company in terms of process safety. But even a company as responsible, as competent, with as good a track record as DuPont has, had a fatal accident with phosgene because of failure of a management system. Go to the Chemical Safety Board website, and there's a video on this incident that talks about the failure of this hose. This hose was supposed to be replaced on a monthly basis. They switched from Maximo to some other management system and maintenance. They switched over, and the hose had not been replaced for 7 months. It was a situation where they'd also looked at alternative controls and didn't implement them for a variety of reasons. Series of management system failures or deficiencies that led to a fatal exposure. Roughly 1 to 2 pounds of phosgene was released, and the fellow who was walking by when that release occurred, he was about 5 to 10 feet away from that hose. Just by chance happened to be there. With phosgene, chlorine's not exactly as phosgene. The impact and the consequences may not be well exhibited for 3 or 4 hours. So he appeared to be fine initially. 4 hours later, started to suffer from severe fluid in the lungs, and he was dead in 24 hours. So these are some of the issues. And again, for those of you who weren't here, OSHA process safety management standards for management systems requires the one's process knowledge. They call it process information. In this list of 20 elements under risk-based process safety, we like to call it process knowledge. To convert process information by having process safety competency into process knowledge, to make knowledgeable decisions about risk. They also, asset integrity and reliability, training, compliance with standards, and making certain that if you had an internal standard to have a Hastelloy jacketed hose, that you in fact have Hastelloy jacketed hoses. And when you look at what are the costs, is it expensive, is it time consuming, is it a pain in the neck or worse, to do that, yes it is. But it's a lot less of a pain than to deal with a 70-ton release of chlorine gas or a release of a couple of pounds of phosgene that can kill someone. Chlorine release another DPC facility in Glendale, Arizona in 2003. Release of chlorine from a scrubber that had insufficient caustic. 5 local residents and 11 policemen treated and released for exposure. Luckily, no one was killed. Now, this is an example of lack of process safety competency on the behalf of the corporation. not having adequate management systems in place, not doing adequate hazard identification, not fully understanding the process in terms of potential consequences. They had not done an adequate analysis when they did hazard identification and risk management of looking at what the potential consequences are. Remember when we talked about, at the earlier session, about propane, those releases and other types of hydrocarbon fuels, and when you look at consequences, are we going to have a jet fire? Are we going to have a vapor cloud explosion? Are we going to have a release of multi-phase and have a fireball? What kind of fire scenario do we have to plan for? In this case, they did not do this kind of analysis for what might happen. So they were going along and they were making a bulk transfer. And on an infrequent basis, they would fill bulk trailers, these over-the-road trailers, from chlorine tank cars so they could make deliveries. And they would purge the system, the tank truck before starting, or at the end, they would do a purge and put the purge gas through a solution of sodium hydroxide to form bleach. And then they could sell the bleach, and they would not have to emit any chlorine gas. So they had done a risk assessment, they had looked at the regulations, and they had put in place a system which was good for the environment, would not waste material, they could sell another product, and everything should work fine. However, they had not looked adequately at how should we control this? What can go wrong? So the CSB concluded that the safeguards provided on this scrubber were not commensurate with the risk. They did not have nearly enough caustic in the system to handle the chlorine. So at some point when you've reacted, when the chlorine hits the water, it forms HCl. The HCl reacts with the sodium hydroxide, and you get the formation of sodium hypochlorite, and you have a situation that's under control. When you no longer have sodium hydroxide available, what's going to happen with the chlorine? Well, it's going to still react with water. You're going to get HCl vapor emissions, and you're going to get some chlorine going right through the system. And that's exactly what happened. And they only had procedural controls, and they had people involved in these operations who were not adequately trained. It doesn't mean that everybody there had to have a degree in chemistry or chemical engineering, but they needed to understand why why things were done in a certain way and what the limitations were. And one of the key requirements is to have safe operating ranges in terms of how much material can we purge from a vessel, how much caustic do we have to have. Totally inadequate in terms of what they provided. More bad news, 2007. Technician error when transferring chlorine from rail car to storage containers in a bleach factory. Over 900 pounds of chlorine gas. Now, most of the accident reports I've seen throughout my career have as the first thing when I read the accident report, operator error. And in too many cases, what was the response? Well, how could they have been so stupid? Let's fire the operator and get somebody else. Let's transfer them. Let's give them more training. When the problem was probably back with the engineer who designed the system, or the maintenance department that didn't adequately maintain it, or the person who wrote the operating procedures. And we talked about multiple layers of protection and making things foolproof, to have connections where only one type of hose can go to one type of connection if it's critical that you have that connection. As an engineer, when I wrote operating procedures for transferring new technologies into manufacturing, I always got it right. I always had every scenario figured out, every contingency, and the operators listened to every word I said, just like you are today. Their wisdom, these golden nuggets when they walked out of the training room. They were ready. You can't depend on a single layer. You've got multiple layers of protection. In this particular case, there were no fatalities. They shut down the port of Tacoma for a number of hours, which was a problem, but luckily it wasn't more serious. Now we'll move on to oxygen and nitrogen. But maybe before that I should ask, are there any more questions? I did not put together examples of all of the many cases where chlorine has been released at water treatment plants, swimming pools, and wastewater treatment plants, because I assume you've heard a lot of those. Those typically are much smaller. I wanted to talk about those situations today where there's a possibility of much larger releases. And also, one of the things, since we've got some new people in the audience, before we move on to oxygen and nitrogen, again, this situation and information about levees. When you have a liquefied gas under pressure and you have a failure of the vessel, you get a very rapid boiling. You get a very rapid phase transition, which can blow the vessel apart. Once you've breached, you have an opening formed. And that's called a boiling liquid expanding vapor explosion. And those of you who weren't here to hear this, I want to repeat it again. In most training courses for emergency responders, and I just checked on the website last week and I saw this same information from a state fire marshal who said levees only occur with flammable liquefied gases. That is absolutely not the case. He is absolutely wrong. There is no technical basis for that statement he has made. It is totally incorrect. Levees can occur with many liquefied gases, including water, under high temperature conditions above its boiling point. There was a catastrophic failure of a water-based process in Gramercy, Louisiana in the 1990s at a Kaiser aluminum bauxite ore facility during the middle of the night because they ran at above design operating conditions on pressure. And that water-based process, which was filled with a caustic solution, essentially water, that vessel levied. There are many instances that have been in the literature, fortunately not a whole bunch, but there are numerous, where there have been levees that have occurred under non-fire scenarios. So that's the other misconception among many, especially in the fire service, that levees are, one, restricted to flammable liquefied gases, and two, that levees occur only under fire scenarios where you have either direct impingement or high levels of radiant heat on a vessel. There are numerous incidents where you can get mechanical damage to a vessel. Now, I have an example here, and I don't know where it is. The example is in the ammonia section. So for those of you who aren't coming, I'm going to give this as an example. Houston, Texas. A transport tractor trailer, and it could have just as easily been carrying chlorine. It happened to be carrying ammonia. The driver took the exit ramp at too high a speed. The trailer went onto the guardrail and the up next to the concrete embankment and damaged the side of the tanker. A long scrape mark, I don't know how many feet long it was, maybe 7 or 8 feet along the side of the tank. The tank then went over the side of the embankment, landed on the highway below. This was an interstate highway, and levied. There was no fire. It was not propane, but it was a levy, immediate release of the total contents of the vessel. So I'll talk about that. So I just want people to understand that levees are not restricted to flammable gases nor to fire scenarios. And there are numerous incidents I also showed in the previous example on propane about situations where there have been levees reported, and the article is in Fire Engineering, and it's referenced on the slides. Now, oxygen and nitrogen. Chlorine is an oxidizer. Oxygen is also an oxidizer. Nitrogen and oxygen are often produced as co-products in air fractionation, distillation at low temperature, cryogenic operations. There are numerous definitions for cryogens. In the state of California now, cryogen is defined as a liquefied gas at less than 90 degrees centigrade. Other codes, other standards may make it minus 150 C. Regardless, it's real cold. When you have oxygen, you can have oxygen in two states. You can have it as a compressed gas, well, you can have three. You can have a non-compressed gas, you can have it compressed, you can have it as a compressed liquid, but it can only be as a compressed liquid, liquefied, at what conditions? Cryogenic, because the critical temperature is well below normal room temperature. So you cannot liquefy oxygen or nitrogen at room temperature. It's only under cryogenic conditions. But oxygen and nitrogen are both used as liquids and shipped and used as liquids or as gases. Oxygen is used widely, and I give this discussion to a lot of different people in different courses and venues just to make certain that these hazards are understood. So this is one that may not apply as much because other than in refining, there aren't as many uses for large tonnages of oxygen in California industrially. Of course, in the medical area, it's just the same as everywhere else. So within your jurisdictions, there probably are compressed gas storage of oxygen, as well as liquefied oxygen under cryogenic conditions in medical facilities, in research facilities, and to a lesser extent in industrial facilities in California. Those properties of oxygen, the boiling point of oxygen is minus 297 degrees Fahrenheit. The critical temperature is minus 181.4. So anything above minus 181.4, it can't be a liquid, no matter what pressure you put on it. Relative density to air, it's pretty close, right? It's a big constituent in air. And nitrogen, which is the other major constituent in air, has a molecular weight that's very close, so it's going to be very close. Vapor pressure oxygen. Again, I put this curve in so you'll have this. And at this point, I did not get a lot of examples of what's gone wrong with oxygen. Oxygen, cryogenic oxygen, just like many of the situations where I talked this morning about low temperature nitrogen, frostbite, oxygen contacting organics, very much accelerates the burning rate. So there can be high hazards associated with liquid oxygen. So I guess I'd open it up to the floor. If you've got any questions about chlorine or oxygen, I'm happy to try to address them. Or you can take a longer break. What's your choice? You want to talk about anything else on chlorine, oxygen? Anything I said this morning? Yes, sir.
After they test those valves, the safety valves, is there requirements?
There is. And it depends on, I'm sorry, I'm supposed to repeat the question. The question is, how often are some of these safety valves tested? And these could be pressure relief valves, these could be excess flow valves, they could be also automatic shutoff valves for emergency response valves to respond to situations where there may not necessarily be a code requirement. So the answer is it depends. And there are a lot of standards, and in most of the standards, it specifies the frequency for going out and testing and inspecting and replacing and changing out. So in many pressure vessels, what you will see is they will have multiple pressure relief valves, or they may have not all are protected by valves. They may have rupture discs. And some may have both, because the valve, they may have a rupture disc to protect the valve from the corrosive contents inside the vessel. And so, yes, there is a frequency and there's a requirement to keep records of those to go out and do the testing. But the frequency, for example, in propane tanks, I don't remember if it's 10 or 15, it's not very frequent, is the answer. Anyone else have a yes, ma'am?
I have a facility that has about 4 tons of propane. It's an unmanned facility that's only accessible by snowmobile in the winter at an area that's elevated over the town. And I'm worried about this. My concern is there any reason why I should push to have them switch to some other form of water treatment?
Now you said propane, didn't you?
No, I said chlorine.
Oh, you did say chlorine. Okay, I didn't hear you. I was going to say, I thought.
I'm so sorry. Chlorine.
Okay. Okay, so how much do they have in the inventory?
At least 4 tons.
Okay, so the question is, for all those, if everyone couldn't hear, so in her area, they have a water treatment plant that has 4 tons of chlorine, liquefied chlorine gas, right? It's a stored. Do they have 4 one-ton containers?
Yes.
Okay. And so the question is, should you push for them to use something else? And of course the answer is it depends. I think that they certainly fall under CalARP, right? So they have been required, and they fall under the requirements to do a risk management plan. And so they have developed a series of scenarios. Is that correct? And so I would go back and explore those scenarios. And is this a public agency?
Yes.
There certainly are alternatives, as you know. And this is one of the easier ones. Now, if it was making vinyl chloride, you've got to have chlorine. But to disinfect water, you can use bleach. It requires a different feeding system. It requires that you haul more material. It requires that you retire a system they've already got installed. So there are all sorts of financial reasons why someone may not want to make this risk-based decision. But this is a perfect example of a situation where there can be a risk-based decision made. And at the end of the day, the risk-based decision may be that you're still going to tolerate that situation. But it would be interesting to see how that decision plays out under more scrutiny. But it's a good question. And I don't know what the right answer is, but it's certainly one worth asking. Yes, ma'am.
At some point, in situations like that, it might become apparent that your efforts are better. They're going to be wasted trying to make somebody change because of the financial issues, and you're better off just regulating the snot out. And make, I'll tell the story because we have time, and I thought it was pretty funny. At our wastewater plant, city plant that did change to sodium hypochlorite in the end, they had a And so their written procedure was, this was in their manual, that you stand outside the room and you go, take a few deep breaths, and you hold your breath and you run in and you adjust the valves. And he didn't quite make it to the door before his automatic breathing response kicked in. And he ended up being fine, although he did spend some time in the hospital. And when he got out of the hospital, they wrote him up for being unsafe work practice. Which eventually, obviously, he rescinded when he briefed it and brought in the directions that
Now, let me make the comment, though, because I was talking about the Chlorine Institute, and I have no involvement with the Chlorine Institute. I have no association. I don't consult for the Chlorine Institute. I'm not involved in any way. And I'm not a proponent for the chlorine industry, but I will say this. On your hypothetical situation, what would happen and should we change? And I'm curious what they did at the facility in your jurisdiction. Did they eventually change?
They changed to both, they eventually changed. And then in the other city I regulate, they had a pool with chlorine, and they eventually changed away from liquefied chlorine. They both made the decision that ultimately the risk wasn't worth it. They planned for it financially. They're relatively well-off agencies, and they did that.
Yeah. So they went to sodium hypochlorite? Yeah, so a solution. And I'm going to talk about that with ammonia and going to ammonium hydroxide where it's possible. So let me say this, though, because I've been involved in a number of designs where you have to make a decision. Are you going to change, or are you going to make the system, are you going to put in multiple layers of protection? If you make that decision, so this question you have asked, the two topics and examples you gave, are perfect examples of making something inherently safer. And one of the risk decisions is substitution or partial substitution to make it inherently safer by eliminating some of the hazard. But you can also get to a similar level of safety in terms of probabilities by putting on additional levels of control. But then the question is, you've got the trade-off, because if you put in additional levels of control, it means you've got additional inspection, testing, calibration, and maintenance to make certain those additional levels of control will respond and perform as designed on demand. And you've got the public perception issue as well to deal with. So there are no easy answers. But I will say this, that I have been involved and I have observed and seen a number of cases where multiple layers of protection have been put in that have worked just fine. So I'm not going to say you should definitely get rid of you should push them to get rid of the 4 one-ton cylinders. There may be ways to put secondary containment, scrubbers in, so they can continue to use one-ton cylinders. But at the end of the day, they may make the risk-based decision that it's not worth it. It's easier to do something that's inherently safer. But there are a lot of trade-offs, and I don't want to advocate for getting there one way or another, because there are different ways to do it. But the thing is, you have to make the risk-based decisions, and one of the 5 T's is, and maybe this is what you should do in your jurisdiction, is to tell those at risk. Because if everyone fully understands what the risk exposures are, and the utility, the public utility that runs the water system, they have a risk exposure in terms of liability. The public that's exposed has a risk exposure, and they deserve to be told. And that, of course, is the whole point behind CalARP, is making certain that people understand the risk exposures. Now, whether or not that communication is effective, and whether or not the public fully understands in all situations what the true risks are, and whether or not they care, is a different situation, because we're talking about potentially high consequence, very low probability events that happen very infrequently. And so it's tough to get people's attention in their day-to-day lives. But that's part of our jobs, to make certain people understand what the risk exposures are and that they make risk-based decisions with some appreciation of what the consequences might be if they don't, with a much less greater ability to estimate the probabilities. And since we've got some more time, I'll tell you a story. There's a fellow by the name of Professor Sandman, who's now retired. He was a professor at one of the universities in the East, Rutgers. And I had him involved as a consultant when I was at a corporation, when I was head of the corporate environmental health and safety and process safety activities. And we had a very well understood, I think, at the company, risk-based decision-making process in doing risk assessments for processes. And we brought him in to help communicate, to help us communicate with external stakeholders on risk communication and what the do's and the don'ts and so forth of how to do that communication. And he told me, he said, as a social scientist, he said, I was so delighted as a social scientist to finally find a field where the data management and analysis is sloppier than in social sciences. And he said, that's risk assessment. And he said, and he challenged me because he said, you as an engineer, he said, you've got all of your engineers doing all of these risk assessments, and I will challenge you to estimate the risk equation more accurately than I can in terms of some of the factors. And he said, your risk equation is this. Your risk score is equal to some probability number times some consequence or severity factor. So it was a 2-by-2 matrix. And he said, I always add the outrage factor. So the risk that's perceived by you as an engineer and all of your scientific colleagues here is probability factor times severity factor. And you have forgotten the outrage factor, which as a social scientist, I can estimate that outrage factor much more accurately than you can estimate that probability of event factor. And he was absolutely right. In most cases, he could do it. And so that again comes down to the part of the answer as to how to deal with some of these situations is, and what makes the outrage factor. And so I would encourage you folks to go and look at the website, type in Peter Sandman, S-A-N-D-M-A-N. And on his website, he has a book that you can download free. It's a pamphlet, it's maybe 30 pages, I think. And he talks about risk perception and how the public views risk and the dreaded risks, those things, reproductive hazards, carcinogens, teratogens, serious inhalation hazards like chlorine. Chlorine's a real hot button. Burn injuries from vapor cloud explosions. So you can take a look at that and get some idea as to how to discuss in a public forum and address this risk factor, which is real, this outrage factor, which is real, and it's not necessarily rational in terms of its absolute magnitude, but it's a real factor. Yes?
Years and years ago, when I worked in Union City, there's a big air plant, air liquefied plant. And in addition to air cryogens, they also have huge tanks of cryogenic hydrogen. And the school district was proposing to build a new elementary school directly across the street from this plant. And we had a public hearing. And the school, the superintendent of schools was there. And he was up at the front answering questions. And somebody asked him a question about, well, how do you feel about this risk? And he says, well, obviously, if they have a problem over there, it's going to fry the school, we're all going to be dead. But, We were sitting there going, really? No, everybody just accepted that with no qualms at all?
Yeah.
No false questions even. We would not have predicted that.
Well, in the discussion this afternoon on ammonia, I can throw in a little story, but I'll tell it now as well. In terms of talking about risk decisions made at public meetings or internally related to children. And one of the decisions that I was involved with at one time was to locate a 500-child daycare center. And during the evaluation of the site, it was found that there were a number of ammonia refrigeration systems in a fairly close proximity, within quarter mile to, or less, very close, within the impact zone if there were to be a release. And so I was involved in overseeing a lot of consequence analysis work in terms of what might go wrong, looking at the probabilities, looking at the industry data. For the last 20 or 30 years, searching the literature, looking at all of the information. So we made the presentation, made the assessment, and unfortunately the property had already been purchased, and a number of things were already in place, and the ball was already rolling. And so the decision was made to proceed, but we decided to put in mitigation measures. What if, even though the probability is low, we did all of the windrows analysis, looked at what percent of the time during the period of occupancy would the wind be blowing in the correct direction to cause an impact. And even though we thought the risk was very low, we had perimeter detectors for ammonia put in place. We had a shelter-in-place plan written and all of the child care staff trained on it. And then we also pushed to have the local CUPA lean on the people who operated those systems to put in place an emergency notification. So everything's going along fine. I had the meetings, we talked about probabilities and how low the probability was of these events, but we've got mitigating safeguards in place. Within less than 6 months after that child care center opened, there was a major release of ammonia. The company that released it failed to follow their emergency plan, give adequate notifications that it had happened. Luckily, it happened around 5 or 6 in the morning before anyone was there. Of course, all the alarms went off. But while my business as an engineer is preventing loss of containment, I'm practical enough to know I've got to have mitigating safeguards in case we lose containment. And that's a perfect example. Low probability event that should happen once in decades. Within 6 months it happened. So, any other questions, comments, observations? If not, let's, I think I start again at 3 o'clock, right? Okay.